Hi, nice to finally be here and see you all today. I will give you a presentation about the topic of dynamic consistency boundary, about the idea, but also about the very particular implementation based on top of SQL database with multi-version concurrency control. And in order to comfortably say about dynamic consistency boundary, I have to go through several topics just to set a correct context. The first topic is the events, the event-driven systems, and in particular event sourcing, because dynamic consistency boundary is linked directly to event-sourced systems. And in event sourcing, that's a very small example. In event sourcing, in such systems, we describe the history of the system by the actions that happened in the past in form of such events in the past tense, holding some qualities. Like here's the example of a system that may be used to, like when you're on a gas station and then there's some prepaid card and you can top up this prepaid card with some credits and then use those credits to buy some things or get rewards. So there are two events, credit top up and credit used, and they all together form a history. And the next stop in that context is streams, because events exist in some groupings. Stream is a grouping of events that share a single quality, like they belong to very particular account ID. Then we can call that the stream that holds any event that belongs to that account. Next up is projections, and projection is a way to say that we transform a list of events, for example, contents of such stream, like contents of those events in account 13 stream, and what we get is some data structure, like the balance of that account. How many credits do we have that we can spend on some things? So we get to aggregates, which is quite a difficult name to say about the tactical pattern in domain-driven design. And the role of the aggregate is basically it's a model. It's a model that encodes some business rules, but also this model serves as a consistency boundary. Everything within the state within should be consistent. And the role of this aggregate is to protect the invariance of that model. And in this particular take, the event source aggregate is backed by the events. The events that are grouped in a particular stream. And in order to work with such aggregate, we have to project that stream into the state. And then any action we take on that aggregate results in an event. That's the event that is describing what happened. If we top up the credits, there is the event that says at the end what's the result of such operation. Finally, there's a thing we have to say a word about. Optimistic locking. It's a technique that gives us consistency in a concurrent operations when we have multiple of such accounts being used at the same time. So I'm not sure if you see it correctly, but in this example, we have two instances of the very same account related to the same account ID. And what we do is we start those two accounts and use credits on first account, and we attempt to use credits on the second account. We base the decision to use credits on particular shape of the state. There was a particular list of events when we were starting that account. We made a decision to use credits, and the first operation to use credits on the first account should succeed because we had enough credits at that time. The second should fail because in the meantime the situation changed. And the way to figure out that something changed is to not only get events but also the last position in the stream that tells us what was the state of the storage at the moment when we were doing the read operation. And then it's the event store of the database that is responsible to compare if the decision that we're presenting was made, the decision that we try to persist was made in particular circumstances. And if those circumstances changed, the event store should fail the operation because something happened in between. And I had to chop this slide a bit, but in an event store that is implemented on top of SQL, the way to provide such safety mechanism is to have a unique index. A unique index on a position in a stream that is in scope of particular name, which means that if there's the append operation, and let's imagine two concurrent update operations, and they both want to append some events that are a result of a decision that was taken when there was a very particular expected position, like the decision was made when there was only one event in a stream and the position of that event was 1. When the insert happens, it starts with that position, and if the second append tries to write to this position that should be unique, it will fail. Okay, and that was a very short introduction. So I could say a word about me. I'm Paweł. I came to you here from Wrocław, where I'm organizing the Dolnośląski Ruby user group. We call it PLRUG for a reason. I'm also involved in organizing Wrocław Ruby conference. It runs for quite a while with some breaks from my side. I've been also involved in Rails event store in the last decade. I was developing it, maintaining it, and became a leader at some point. So if you have the chance to use Rails event store, we had something in common. Okay, so finally, dynamic consistency boundary. I struggled a bit about the topic, how to present it most precisely, or maybe what's the best angle to present it. And then I've seen a presentation when someone approached it from the context of comparing to the aggregates, but in a bit different way. With event source aggregates, our consistency boundary, how we look at this consistency boundary, is formed by the model. It's the model that defines that boundary, the shape of it. With dynamic consistency boundary, the boundary is defined by the use case. So we approach it from a different side. A use case could be a part of that model that we've seen before. And that has some very profound consequences. Let's take up the first example, topping up credits in the account. That's the whole logic to top up credits. If we made a event source aggregate by using the event store that is stream-based, we would probably model it as an account that projected states from two events, credit top up and credits used. And there's the operation to top up credits. As we look into that operation, there's no particular and very interesting logic there. There's no balance that we depend on. There's no limit to make the top up. It doesn't make any difference how many times we do the top up. It's a very simple logic. But because our consistency boundary was defined by that object and influenced by the object-oriented design, we have to load all those events and source the state into that balance only to make a decision that doesn't depend on them. So there's the first waste in that situation. The very rigid consistency boundary that was defined for the model doesn't work well for that particular operation. It becomes a waste here. Then there's the second operation, using credits. Now we have finally some logic. We cannot spend more than we have. And that's very reasonable logic. And for that logic, we do have to source from all of the events related to the account. And we do have to project to have a balance just to make the very decision whether it's allowed to use those credits or not. And it looks okay. But then what happens when we take a decision to use credits and in the meantime someone tops up that account? It shouldn't have any influence on the on the operation of using credits. The more balance we have, the better is for us. We already verified that there's enough balance to use that many credits that we want to use. So it shouldn't be the operation of topping up in the meantime while we use the credits shouldn't influence using the credits. And because of the consistency boundary that we formed around the account, it actually matters, because once you append an event to that stream that comes from topping up credits, it will fail the operation of using credit that happens in parallel. It shouldn't, but the consistency boundary here is just too wide for that single operation. Ideally, it would be only credits used that fail the operation, because that means that the balance decreased and maybe the rule is no longer fulfilled. And by the way, those two examples with credits top up and credits used come from Mateusz Nowak from blog Na Kodach. It was a very nice example that he presented that resonated very well with me. This example comes from Sala Pellegrini, and she described this whole idea of dynamic consistency boundary. And the starting example was something like this. Imagine we have a situation where students can subscribe to courses, and there are two rules. A course cannot accept more than 20 participants, and student cannot join more than 5 courses. Seems deceptively simple, however, and the code sample won't be very readable. So try to talk about it. So if we try to model aggregates to support that situation, we can go, there's a whole spectrum. You can go to the very left of the spectrum or the very right of the spectrum. And trying to follow the rules from the blue and the red book, we would probably start with very small aggregates. The smallest we could probably get to support the idea. Unfortunately, the smallest aggregates that we could think of would be a course and a student, each of them protecting the very single rule, like the course protecting that there are no more than 20 students, and the student aggregate protecting that there are no more than 5 courses that the student is subscribed to. And it is a problematic situation, because when you're subscribing to a course, we have to fulfill 2 of those rules of those 2 aggregates at once. And if we try to follow another rule that the results of one aggregate operation can influence the other aggregate only in eventually consistent way, you could imagine that the only way to fulfill that would be to put something in between those 2 aggregates, some kind of process or a saga. And unfortunately, putting a process in the middle of them makes this situation just more complex. And I'm afraid it is not essential complexity, but rather accidental to introduce such process or a saga. Because if the first aggregate succeeds and we notify the other one to perform the operation, if the operation on the another one succeeds, we're good to go. But if the second one fails, we have to reverse the operation and make some compensation on the first one. It just makes the whole operation a bit complex, and we're still within the same bounded context. That's why I don't think the process is suitable here. On the other side of the spectrum, we could design an aggregate that can verify both of those rules when subscribing. But that also means that the consistency boundary of such aggregate is very wide. We have to know about all courses and all students. And in a situation where the system has to perform well under stress and under concurrent load, it would be a disaster. I have one story to tell from my past when I was designing such system. And the aggregate was a campaign. The campaign was responsible to unlock some seats on a stadium. Like you had a campaign to unlock 500 seats. And finally, that campaign was used on a match day. There was a Europe League match. And as you can imagine, the guests that wanted to buy such a limited number of tickets were fighting for them. And the system collapsed because it was too much of the load and too much contention for such a big aggregate. And my learning from that time was that the right boundary was just a single code. I wanted to encapsulate all within a very big aggregate, but I didn't pay attention to the consistency boundary. So it was a good lesson to me. And from now on, I'm thinking about those boundaries. So what we can do about it? And there's the practical use of DCB, and the examples will be with the small gem EN57 that actually didn't exist before Wrocław RB conference. And EN57 is the name of the electric train, elektryczny zespół trakcyjny, which was produced in Wrocław, in PAFAWAC factories, and it's actually the longest produced electric train in Poland and in the world. That's the story. Okay, so dynamic consistency boundary. Remember that we focus on the operation. The consistency boundary comes from the operation. So here we focus on an operation to use credits. There are three things to focus on: tags, types, and the append that is a bit different from other event stores. There are no streams in dynamic consistency boundary, but we still have to figure out we still have to figure out what events are related to each other. And for that purpose, we use tags. Events tagged with the same tag have something in common. Here, those events share a single account ID. Because we want to work on a minimal set of events that is suitable to perform an operation, we specify which types of events are we interested in. This is using credits, and here we have to use all of those events. But we remember that we want to work on a minimal set of events, only those necessary to perform the operation. We have only one operation, so we don't have to care about other operations that extend our scope, like that happened earlier in the model. So once we have those events, once we have the position of the last event in that query, we could evolve, which is just a projection, evolve those events with some initial balance to figure out what's the current balance that results from those events. And then we could perform the operation, decide. Command is our intent. Use credits. Balance is the state that we base our decision on. And the result of the decision is just a list of new events that we want to append. Appending those events is like making everyone know what happened and that's persisted in the system. And the biggest change when thinking about the stream-based event stores and DCB-based event stores is how this append operation is shaped. Because for the optimistic locking part, here in DCB, we perform a query. We perform a query because the consistency boundary is not related to the model. It's not rigged. It changes from operation to operation. And for this particular operation, we want to fail only if there's a new credits used in a list of events that are in our scope, that is, they are tagged with our account ID, and only if that is after position of the last event that we've read. So if we execute this query just before the append, and we find a credits used related to that account, we would fail the operation. But if not, we're good to go. So that's the second part where we adjust the consistency boundary just for this operation. And for this logic to use credits, we only have to figure out if there were any credits used. We're not interested in credits topped up. So if there's a concurrent topping up of the account, it would not fail this operation. So again, second win. But I know what some of you may think. How is adding a query just before the append a better situation, additional thing to do? And the second very tricky part is how to make sure that this query just before the append doesn't introduce any race condition and inconsistency in the system. Okay. So that's when we go from the idea to implementation. And these are just the two ideas that you could do on the Postgres-based event stores that use DCB. They both share something in common. They are a form of locking. An implicit one with isolation, with serializable isolation level, and more explicit with advisory logs. The serializable isolation level is an isolation level of multiple concurrent or parallel transactions that says that transaction can run in parallel only if the result of such run is if they would run serial one after another. If that condition is satisfied, they're good to go. And Postgres has this algorithm called predicate locking, where it marks some parts of the data that were read, flags them, and if there's a write operation that would change that part of data, it raises serializable error. That algorithm is some approximation. It doesn't work on like concrete values that we use in a query. It's rather like it uses some parts of the index, particular leaves of the binary tree that forms an index. So it has some false positives, but it's a compromise just to make it more performant. With advisory logs, the idea is that, the idea with serializable isolation level and the query in the append is that if we run a query that checks for some particular events, if we are appending those events, we would flag those areas in indexes and fail the transaction because a write would affect a previous read. With advisory logs, the idea is that we take criteria from the append query, from the append condition, and for each of those criterions, we do set a log. So if there's another append query that reuses some parts of those criteria, they would line up and linearize because of those logs. Okay, so yesterday I was doing benchmarks all the day just to present some. I was really curious because I had some idea how it could look like. I was expecting the worst, but then even for me it was a surprise. For reads, I'm comparing here reading from the blue one is the stream-based event store, the green one is tag-based like the DCB event store. And what I wanted to see in that kind of benchmark was for the first thing, if there is a difference between two implementations and the streams and tags are not very far away. So there's really no difference between them. But I was also curious, what's the number of events that matters? Doesn't matter if we drop some events if our stream size was about 10 events. It doesn't make, there's no big change between 1 to 10 events in a stream. And even up to 100 events, whether it's a query that takes 100 events or a stream that consists of 100 events, that's not a big difference either. I know some people do work on very large streams. That situation with the football club taught me that I should prefer smaller streams. And that's why I kind of figured out that balancing between 1 and 100 is probably the best size of that stream. And I think there are situations where reading less than more events from the database could have a bigger impact. This was benchmarked on my local machine, so there was quite a good connection on the socket to the database server. I would guess that a more remote server or a network with much smaller bandwidth would have an effect. I was benchmarking on quite a small event sizes. I would expect that much bigger event sizes would influence the benchmark much more. And the third thing, which could have the most influence, is that I was only measuring reads from the database. There was no deserialization of that payloads into the application. And I think in most of the applications, that's the real cost of reading events, because deserializing big payloads, especially if they are decorated with some kind of library like dry struct or dry types, takes a significant amount of time and pressure on the memory. So that's the situation, I think, where reading less, especially if we don't need that events, would be a big benefit. Okay. For the right part, I've performed 2 benchmarks, one in the most happy situation where there is no conflict, and the second one in the worst situation where there's always a conflict, like 1 of 10. There were always 10 concurrent writers. Their task was to write 100 events to the event store. When in a situation with no conflict, each of them should succeed. There were no interdependencies, so they could run in parallel. And this is how the results look like. Stream append is like the regular stream-based event store. DCB append is an event store that uses serializable isolation level, and DCB log is an event store that uses the technique with advisory logs. And to my surprise, first, the logged version doesn't differ that much from a stream-based version, so that was my biggest surprise, and that gave me a hope that maybe it might be fine to just switch to DCB-based event stores. And the results of DCB append with serializable isolation level were also curious. But then I've read about the algorithm that Postgres uses for serializable isolation level, that predicate locking. And it turns out that the reason for such high value for such latency was that I was appending non-depending data, but the data was so similar, like it was the next version numbers or very similar strings, and probably they all went to the same leaf of the index of the binary tree, and that caused false positives from that mechanism. So with more data, probably with much larger database and much more fragmented indexes, it would be better. But for this situation, it looks like the serializable performs very bad. It should improve over time. The second situation, so all conflicts, only one succeeds, so the others have to retry the operation, reread the stream, retry the operation, probably fail as well, because only one of them succeeds. 1 of 10, 1 of 9, 1 of 8, and so on, until there's only one left. And here the constraint on the database performed well. Both DCB implementations, I would say they are quite similar, although there are some variances. But one thing to remember here, with DCB, we want to reduce the consistency boundary, thus reduce the possible contention. So overall, we should be getting less conflicts than on stream-based event stores. So even if the situation seems like worse in all conflict situations for DCB-based event stores, I think from the real-life world, it would be more balanced. At least that is my intuition, not backed by the data, because I don't have the data yet. Okay, so all of these examples and benchmarks are to be downloaded, to be executed, to be debated, because I'm curious. Benchmarking is an art of its own, and if someone can do it better, it would be of my benefit too. So to recap, the idea is that dynamic consistency boundary focuses on a use case. It's a boundary formed from a use case perspective, not from a model perspective. That's why it's a bit narrower. It promises us to only work on the absolute minimum set of events that are needed for particular operation. And it also promises us that the consistency boundary would be the smallest possible as well. So we should be getting conflicts from too wide surface area. There are 3 things that an event store should implement if it wants to support DCB. That is tagging the events, filtering events, and filtering by those tags, filtering events by types, and the append that allows to run a query so that the boundary could be adjusted. Okay, and there's one final remark, because it seems like you could implement aggregate roots using decider, and that parts of the decider, like compose something bigger from something smaller. It also seems that you could emulate stream-based event stores from the parts that DCB has. So eventually, if you're working on or using any stream-based event store, you could probably have a DCB implementation underneath. And if the performance turns out to be as great as the stream one, you could have the best of both worlds. Compatibility with stream-based event stores, and chance to use DCB fully on the new ventures. And there's a set of additional materials. There's quite a lot of event stores that implement DCB already. There are 2 in Ruby. The first one is mine, and it's quite new. It's experimental, and you should probably not use it. The second one, Chronico, is much older, and it has a different idea. It's file-based, not database-based. The UmaDB is the gRPC one, so you could probably generate bindings in your language. That one is in TypeScript and very nice ideas around it. The most commercial one is in Axon IQ, and I think they were releasing, or they are releasing, the Postgres version in the next days. And that one actually is the nicest API I have seen in a while, the Elixir one. There's a lot of interesting articles from Mateusz, from Sarah, a podcast that I recorded with Mariusz, and the main site for DCB, where's the whole specification if you want to play with DCB. It like breaks it down into the smallest details there, and there's a lot of examples. So there were no questions so far. I'm ready to take them now.